Well, I don't know what happened last time. I've given that lecture before, and it came in right on time, and I ran over. I must have gotten really excited about the history of geology. I hope maybe you did too. So what's going to happen today is I'm going to give you the rest of that lecture, and it's repeated here, so you don't need to get out the old handout. And then I'm going to go on and show you something new, and it's a brand new lecture, or half lecture. And the idea for it came to me last night, kind of late, and I finished that lecture about 45 minutes ago, just in time to meet with Ryan and David. I don't know if any of you have ever had that experience of going into a test just barely having finished studying, or not quite. Well, you know, professors have that experience too. And so this may not be a polished lecture, but I guarantee you it's fresh. So let's go and finish up what we were talking about last time, which is my argument with my friend Enrique Letao from Lisbon, that geology has a much longer history than people usually think. It doesn't just go back to 1800, it goes back to probably 1500 or something like that. So here were the conclusions from what we got to last time. The Portuguese voyages of discovery marked a real revolution in understanding the Earth. In other words, their geology. And they pushed the founding of modern geological science back earlier than the founding of modern astronomy and physics. Take that, right? Okay, so what I want to do now is to go even further and make the case that maybe modern science didn't start with astronomy and physics in 1600. Maybe it started with geology in 1400 and something. So this part would get real objections from people in other departments, but you aren't in other departments, so here we go. So what I want to do now is let's see, how do I work this? There we go. Okay, so there are going to be two parts today. The first part is going to be a continuation, or what I should have finished last time. Should the Portuguese voyages of discovery be taken to mark the scientific revolution, a century before Copernicus? And then we're going to go on afterwards and look at how geologists went beyond just finding out what was where on the Earth, which the Portuguese did, and finding out that Earth had a history. So that's what we're going to be doing. So let's look into this matter of whether the voyages really were the scientific revolution before Copernicus. And just to show you that we aren't the only people thinking this way, here are just some references, just glance at some titles and you'll see. So here's one from 1966, Portuguese Nautical Science and the Origins of the Scientific Revolution. So this idea has been around quite a while. Science in Manueline style, remember the Portuguese Gothic. Here's one called The Portuguese Discoveries and the Rise of Modern Science. This is by a Dutch guy. This is I forget what, Winius. Portugal and the Dawn of Modern Science. Here's another one by a Spaniard with a really combative title. Iberian Science in the Renaissance. Ignored how much longer? You want to get heated up about this, read that paper. Here's another Spaniard who writes, Experiencing Nature, the Spanish-American Empire and the Early Scientific Revolution. And here's my friend Enrique publishing, it's now out, Maritime Discoveries and the Discovery of Science. Pedro Nunes and the Early Modern Science. So we're kind of looking in the same way, and this is not something that is in the way that historians of science think now, but maybe they should. So let me show you what we're thinking about. So I want to tell you about, first of all, something that I like to call meta-scientific discoveries. Meta meaning beyond. You know, metaphysics is what's beyond physics. For me, meta-scientific discoveries are discoveries that are greater than any single revolutionary discovery like evolution or plate tectonics or relativity or quantum mechanics. Meta-scientific discoveries are even more fundamental and basic than that. So here's what I have in mind. They're greater than any single scientific breakthrough like evolution, plate tectonics, or quantum mechanics. And these are the discoveries that have made science possible. You know, for most of human history, we didn't have anything at all like modern science. And so modern science has been made possible by a set of discoveries about nature and what nature is like. And what are those discoveries? First of all, that nature is orderly and not capricious. You know, nature doesn't just decide, well, I'm angry at Walter today, I'm going to make his life miserable by having his car rise up in the air and fall down on him. You know, nature doesn't do that. Nature obeys certain laws. Okay, secondly, and I don't think anybody would have guessed this, but nature's native language seems to be mathematics. Now, who'd have thunk that? I mean, a little child wouldn't imagine that. I don't think most people in the hunter-gatherer societies would have thought that, even if they'd had any idea of mathematics. So isn't it an amazing thing that you can write out these equations of physics and they describe what nature does? Who'd have thunk it? All right, so that's a meta-scientific discovery. Now, the next thing is that you can have a conversation with nature, you know, through experiment or observation. You take something here and you say, okay, nature, what will you do if I let go of this thing? And you let go, oh, it fell. That's what nature does. So you can ask nature these questions. That's what we're basically doing in both experimental science and observational science. I mean, that was an experiment you just saw, not a very sophisticated one. But also, when I go out and observe rocks and make measurements on them in the field, I'm asking questions of nature. So that's a conversation. And then finally, the one that's down at the bottom here, it said, the results of experiment or observation must take precedence over the statements of authority. And at the time when science was emerging, authority was spelled Aristotle. And that was the greatest scientist of antiquity. And if you wanted to know how things were, say in 1400, you go read Aristotle. And Aristotle tells you, and authority is what's important. But what they found out in the scientific revolution was that Aristotle wasn't always right. And what you have to do is to go out and make your observations, and then if they disagree with authority, well, tough for authority. So let me go through those just very briefly, and I'm going to concentrate on the last of the fourth one. So first of all, nature is orderly, not capricious. So here, remember, this was the Portuguese sailors sailing to Cape Bojador and then coming home in a great big circle by going way out into the Atlantic, where you really wouldn't go if you didn't have a good reason for it, and being convinced that this pattern was going to continue, that nature wasn't suddenly going to turn around and blow everything the other direction. So these were, the Portuguese understood that nature was orderly, and they were willing to trust their lives to that observation, which is what you did when you sailed out into the Atlantic. Okay, point number 2. What happened here? Oh, did I lose something? Excuse me. Went the wrong way. That's what it was. Okay, so second thing, nature's native language is mathematics. Okay, my friend Enrique has spent a lot of his professional activity studying the works of this man, Pedro Nunes, from the 16th century. And he was a Portuguese mathematician who placed navigation on a mathematical basis. You really can't navigate if you aren't thinking numbers and calculations. And he was the guy who figured out how to do this. And Enrique makes the point that in the 16th century, this guy in Portugal, in little Portugal, you know, usually obscure Portugal, was maybe the #1 mathematician in Europe. In the generation or the century before Newton took over. But here's a quote that Enrique likes to put out. So this is a letter from a man named John Dee. Okay, he was a big guy in England. He was the cosmographer to Queen Elizabeth I. And he's writing to Mercator, who was the great German mathematician who figured out the Mercator projection. And listen to what he says, because Enrique makes the point that this shows with what high regard Nunes was held by people in a country like England. So he says, he writes, he's writing to Mercator, he says, "And if my work cannot be finished while I remain alive." He was afraid he was about to die of disease. It turned out he didn't, but this is what he wrote at the time. "I have bequeathed it, my work, to that learned and grave man who is the sole relic and ornament and prop of the mathematical arts among us, Dom Pedro Nunes of Salacia," that's in Portugal, "and not long since prayed him strenuously that, if this work of mine should be brought to him after my death, he would kindly and humanely take it under his protection and use it in every way as if it were his own, that he would deign to complete it finally, correct it, and polish it for the public use of philosophers as if it were entirely his." So Enrique's point is that at the time of the voyages in Portugal was this amazing mathematician who this Englishman, and presumably the German as well, looked up to as the top mathematician. So the Portuguese were doing the mathematics also. Okay, let's go on to number 3. You can have a conversation with nature through experiment or observation. They were doing this too. Remember, the nautical astrolabe was what they used to determine what their latitude was when they were sailing out in the Atlantic far from land, and they really didn't have any other idea where they were. So they were making these observations and again trusting their lives to those observations. Okay, the fourth one is the one that I want to spend a little time on because I find it so fascinating. The point is that the results of experiment or observation must take precedence over the statements of authority. So let's look at this. Authority, remember, is named Aristotle. And here was what the great authority said the earth was like. So this is from Aristotle's Meteoritics, I think, or is a name something like that. And what Aristotle thought, he knew, of course, that the earth was spherical. All the educated people did. And he thought that there were 5 climate zones. Okay? What are there? First of all, up in the top, there's an Arctic zone which is uninhabitable. Human beings can't live there because it's too cold. And they found this because as they went north, farther and farther and farther, it got colder and colder and colder, right? Okay, so then there was a northern temperate zone that was inhabited, and inhabited by excellent people like Greeks who thought about things, and that's where everybody lived. Now, there was also an equatorial desert belt, and they knew about this because as you went further south into the Sahara, this was known, it got hotter and hotter and hotter. And the point was, they thought that when you got to the equator, where the sun was directly overhead, the heat of the sun would set the sails of your ship on fire. It would burn up, you would sink, and you would be lost, right? So you couldn't get across the equatorial belt into the southern hemisphere. Now, in the southern hemisphere, there presumably was a southern temperate zone, and maybe it would be inhabited, although how anybody ever got there, I guess Aristotle wasn't sure, and there wasn't any way to check because you couldn't get there, right? And then finally, in the South Arctic, there was an uninhabitable cold zone. So this was Aristotle's 5-zone theory of the climates of the earth. That is authority. So if you are a scholar in 1400, this is what you know to be true about the climates of the earth. Okay, so let's see what happened. Okay, so here we have the situation when the Portuguese voyages are starting. Here's Spain, there's Portugal, there is Sagres. Remember, this is where Prince Henry the Navigator had his headquarters and brought all of these map makers and instrument makers and navigators and shipbuilders and explorers. And what they tried to do, what he kept asking them to do, was to go down the coast and go further and further, and they couldn't get past Cape Bojador. We talked about that last time. The problem was the winds were blowing the wrong direction. They didn't think they could get home. But once they figured out they could go in that big loop, they got past that. And so the passage of Cape Bojador took place in 1434 by a ship's captain who's, all we know about him is his name. He was one of Henry's people. And he passed Cape Bojador in 1434. And From that point on, the explorers would push farther and farther south because they knew they could get home. And what would happen is that as they went farther south, they're along the coast of the Sahara here, it gets hotter and hotter and drier, and it really looked like Aristotle was right. But somehow these guys had the guts to keep going and not turn back for fear that their ship would catch fire. And what happened next was utterly astonishing. 10 years after Eonish at Cape Bujador, they discovered that there was something else down there. What is this? This is forest, indeed. And there's rainforest down here. This is, and it's full of people, and it's full of animals. And it was reached in 1444 by another one of Henry's explorers, Dinis Dias. And it's called Cabo Verde, the Green Cape. So for me personally, I don't know if anybody else thinks this, but for me personally, that name marks the death of understanding nature by authority. Because Aristotle said nobody could live there, and the Portuguese went and looked, and what they found was that not only could people live there, but animals could live there. It was abundantly full of people, full of vegetation. Aristotle was wrong. So that's what happens to authority when you go and look. And so for me, again, these two places mark the primacy of observation over authority, the first key element in modern science. So let's look what happened then to the understanding of the world. So this was what Aristotle thought, and it turned out to be wrong. There were not 5 climate zones on the planet. There were actually 7. So Aristotle was right to about there, and his presumption was right the other place, but there was this equatorial belt that was densely inhabited, and you could get past there to the other side, and so it just utterly changed things. So here again is this summary of the meta-scientific discoveries. They're greater than any single scientific breakthrough, and they are the discoveries that make science possible. First one is nature is orderly and capricious. These are what we scientists, even though we don't think about them very often, this is what we're basing our activity on. These are our assumptions. And they're good, seem like good assumptions because they've been demonstrated over and over again to be correct. So the first one, nature is orderly. Yes, the Portuguese understood that. Nature's native language is mathematics. Yes, the Portuguese understood that. You can have a conversation with nature through observation and experiment. Yes, also. And finally, the results of experiment or observation must take precedence over the statements of authority, and that's what Dinis Dias proved in 1444. Okay? Take home points from what we've done yesterday and up to now. I maintain then that geology is the critical science of the 21st century because we only have one Earth and we dare not wreck it. Secondly, geology has a long and noble heritage. The scientific revolution of Copernicus revolutionized geology as well as astronomy and physics. And modern geology goes back a century further than the Copernican revolution. It began with the Portuguese voyages of discovery, and finally, the Portuguese voyages of discovery may well mark the beginning of modern science itself. Modern science began with the study of the Earth, with geology. So there, and someday I'll tell you what I really think about it. Okay, so now let's take a silent moment to refocus, and we'll go on and I'll show you my new thing that I want to talk about. We've got something about Galileo in the paper that we wrote about the Copernican revolution. So I didn't hear because it wasn't enough time, but it's very important. You're absolutely right. Oh yeah. If you ask me afterwards, I'll give you my paper, the paper that I did with Enrique on that, and you can read that. Sure. Okay. Okay. So here's the new topic for today. Remember, we're moving into the earth science, the geology part of this course. And we're going to be talking about the history of the Earth, what has happened to the Earth through time. And in order to understand the history of the Earth, you've got to, first of all, know that it has a history. And second of all, you've got to be able to figure out how old different things are. How old is this rock, and therefore how old is are the events that it records. And so what I was going to do, I was going to give you the usual lecture that a geology professor gives about how you date things, you know, fossils and radiometric dating and all that. I had it all ready. Yeah, I was pretty well ready to go. And then last night I realized, no, I don't want to do that. I want to do it in a different way. Since this is a course in big history, about all kinds of history, I thought I would rather show you the history of how people figured out that you can date things in Earth history, and you can determine Earth history. Who would have imagined that? Because, you know, up until a couple hundred years ago, when you talked about history, that meant what was recorded in books. So how could you possibly figure out what had happened to the Earth before there were any people around to write books? And so I thought I wanted to do this in a historical way, and to have fun with it, I decided that I would focus it around two Italian geologists that I find fascinating, or I should say geologists who worked in Italy, because the first of those was actually a Danish guy. You will be reading a slightly different version of this when you come to read part 3 of the Mountains of St. Francis. By the way, has anybody gotten the Mountains of St. Francis yet? Okay, remember, we're going to be starting doing that. I should have warned you a week or two ago, but if you're going to buy it, go online and see if you can find a cheap copy somewhere. If not, somebody remind me that I need to check in the library whether there are copies on reserve. If they're not, we'll make sure. Ryan's taking a note. He's going to remind me, I think. Okay, so anyhow, I want to tell this story in a way that's personal, because it involves the things that I've done in Italy, and it's based on these two guys. The first one, Steno. Almost every geologist has at least heard of Nicholas Steno. The other one, Ambrogio Soldani, Millie and I found out about 3 years ago. I had never heard of him, and I have come to think that he was really fundamentally important in the kind of things that I've worked on. So I want to tell you the story in that way. Okay, so we're going to go to Italy. How many of you have been in Italy? Okay, chances are most of you have been to Rome. This is going to be a story of 4 cities. How about Florence? Anybody been in Florence? Okay, some people have been in Florence. Okay, how about Siena? Okay, anybody been in Gubbio? We're just kind of getting more and more obscure as we go along. So these are going to be the places that we'll focus our story around. First of all, a briefest mention of Rome. Then we're going to go to Florence. Then we're going to go to Gubbio, and finally we're going to go to Siena. And remember, the point of all this, part of it is to have the fun, the enjoyment of a little travelogue, but also the point that I'm trying to make here is to show that it took great geologists to figure out how you could read history written in rocks. And so these two guys are my examples for today. Obviously there are other people involved in it, but these I thought made a good coherent story. So anyhow, we won't spend any time in Rome on this particular trip. It doesn't have too much to do with this particular story, but it has another wonderful story of Earth history about volcanoes in Rome. So when you start reading the Mountains of St. Francis, this portion of it here will be all about Rome and about the volcanoes of Rome. Sometimes they give a lecture about it, but it doesn't look like there's room this year. So instead of hanging around Rome, let us go to Florence with its magnificent late medieval and Renaissance building. This was probably, it was fair to say, this was the intellectual capital of the world for at least the Western world, for a couple of hundred years in Renaissance times. And fittingly, some of the most important early discoveries in geology were made there. And they were made by this guy, So he was a Dane. He was born in Copenhagen, and his name in his birth name in Denmark was Niels Stinsen. But he became a scholar, actually a medical anatomist, and it was the fashion in those days to Latinize your name. And so Niels Stinsen became Nicholas Steno, or in Italian, instead of Steno, they say Stenone. But he's the first hero of our story today. And he was the guy who discovered that Earth history is written in layers of rock. And I find myself imagining sometimes, wouldn't he have loved the Grand Canyon? With these wonderful, look at the layers running across there and across here. You can see that layer running across and little finer layers in here. This one continues over onto the other side there. This was what he figured out. So stratigraphy is the branch of geology that studies history written in rocks. And Nicholas Steno is absolutely justifiably considered to be the father of stratigraphy, the founder of it, the discoverer of the main things that we use to understand history written in that way. So let me tell you the story from this standpoint. So in the Middle Ages and in the Renaissance, people who went out and wandered around in the hills, and thoughtful people of all kinds, knew that there were strange things out there in the world that you could find in the hills. And these, for example, are tungstones. And there were lots of others, and some of them looked remarkably like the shells of animals. You know, there were curly snail things, and there were clam-like things, and there were coiled things, and all this stuff. And what could they be? So there were two lines of thought on this. One line of thought was that they were the remains of animals who had once lived. But most people didn't accept that. Why didn't they accept it? It was because in those days, the best information that anyone had about the history of the earth was contained in Genesis. That's where you found out what had happened. And you would go and read things, and it would say, let's see, God created the earth on the first day, I think. And somewhat later, he created the animals. But what you'd find if you went out in the field and looked at tungstones was that they were inside the rock or inside the sediment. So if they were formed on the fifth day or the fourth day or whatever it was, how could they be inside the rock that was formed on the first day? So there were a lot of arguments like this that made it very clear that these things could not be the remains of animals. What were they? Well, they had a wonderful term for them. They were called sports of nature. And I guess what that meant was that nature was having a good time making things that looked like animals or animal shells just to confuse people. And, you know, maybe that's not too unreasonable. Today we wouldn't accept that, but, you know, in 1600 maybe people would, because so very little was known about what nature can and cannot do. And so most people at the time thought that tungstones and the other things that looked like animals were sports of nature, and they were completely inorganic. And Steno showed that that was wrong. And what happened was that, remember, he was from Denmark, and he was an anatomist. He turned out to be the finest anatomical dissector of his generation. And so, I love this concept. He would go to a new city, and they would bring in a cadaver for him to dissect, and all the intellectual people of the city would come, and they'd all sit around and watch this because he was such a fine dissector. And so he was the go-to guy for this sort of thing, and he ended up, after going to Paris, he went to Florence. And Florence, as I said, was the intellectual capital of the time. The Medici Palace had the greatest scholars of the world in it at the time. And something happened. A great white shark washed up on the beach of Tuscany, not too far from Florence. And the Grand Duke was told about it, the Medici Grand Duke, And he said, well, bring it to Florence and we'll have Steno dissect it. So they did that. I believe it was in the summer, and probably it smelled pretty bad, but people put up with that. And what Steno recognized was that in the mouth of this shark, and this is Steno's drawing, were tongue stones, just like this. These were the teeth of the shark. It was just absolutely clear that tongue stones were shark's teeth. And so Steno then decided to go out and learn more about these things that called fossils. Fossil comes from the same root as fosse, which means a hole in the ground. So these are things that you can dig up, right? And so Steno went out and he started exploring Tuscany and finding more and more evidence that fossils just had to be organic. They couldn't be sports of nature. And there's a whole list of things I won't go into. But at any rate, he utterly convinced himself these had to be organic remains. But as an anatomist, he had a real good eye for geometry and relationships between different things in the body as he dissected it. And he became the first anatomist of the earth. And what he showed was that there were layers and layers and layers. And he was the first person to realize what now seems to us quite obvious, and that is that if you have a series of layers, one on top of the other, the ones on top are younger and the ones on the bottom are older, and so therefore there's a sequence of historical events. You've probably seen this. You've probably at some time in your life cleaned off some old paint on a wall and seen that under the layer of white paint there's a layer of orange paint, and under that is some chartreuse green from somebody who had had terrible taste, and under that is some brown paint and some more white paint, and they're layer like that, and it's recording historical events. So this was the discovery that history is recorded in solids. And I like to say that the history of the earth is written in solids because liquids and gases forget, but solids remember. They stay the same way they are for years in the case of the paint, or millions of years in the case of the rock. And so Steno started putting together an understanding of what the geometry of those layers meant in terms of history. Here's, I meant to show you this, just, oh yes, okay, so this is the sort of thing that he would say. So he understood that fossils are long dead animals, so therefore he realized that if you found marine fossils on the land somewhere near Florence, that meant that that land was once covered by sea. Otherwise, the fossils couldn't have lived there. So he realized that there had to have been times in the past when what is now Tuscany, around Florence, had been underwater. And he was beginning to read history written in rocks. So now he drew this amazing diagram that I'm going to show you in a tiny bit of detail. But first of all, I want to say that sadly we don't know all that Steno knew. We don't know everything that he understood about reading the history of rocks, because he didn't complete his great work. He planned a great, what he called a dissertation. It was going to be the whole discovery of how you read history in rocks, and he didn't write it, and I'll show you in a moment why he didn't write it. But he did write what he called a prodromus, which is like a little preface, a little synopsis. And we have that. So we have some idea what he knew, but I just wish I knew what was in Steno's mind as he wrote this little brief. This is from the prodromus. This is a series of diagrams, and they're very strange looking. They look like planks or boards or something, but they are a highly simplified, a scientist would call them a model. It's a simplification of what he was seeing in the field to make it clearer than trying to draw all the details of how the rocks are folded. So if we start over here in the lower right, you start with a series of layered strata, layered horizontal rock layers. And Steno figured out that rocks, for the most part, are probably deposited originally in horizontal or nearly horizontal layers. And so that's what's going on there. And then he had to explain some strange things, like up here he saw tilted layers, and now we know that that's due to folding. But he had an idea that maybe what had happened was that somehow the part of that had gotten hollowed out, he didn't know how, to form a giant cavern. And we know that that's not correct, but when you read the Mountains of St. Francis, you'll see that I came to realize while writing that book that he was on the right track. That in fact, if you allow him a couple of little adjustments in his view, it's very close to what geologists think at the present time. There was never any open cavern like that because the rocks would collapse as the cavern was forming, but you'll see when you read it. So anyhow, his idea was that there was a cavern. So now, see, there's one layer of rock across there, and then these other layers somehow end because this area has been hollowed out. And quite rightly, he realized that rocks aren't strong enough to stand up over a broad area if there's something hollow underneath them. And so the next step then was that the cavern collapses. And you get some of this bed here gets tilted down. And that was his explanation for why you see beds which had originally been horizontal and which now are tilted. As I say, today what we realize is that happens is that they get folded like this. They get pushed and folded. Okay? So then what happens? So now you've got this kind of a collapsed valley here, and new strata are deposited in it. So he saw that there were places where there were horizontal strata that were up against tilted strata like this. And then the next thing that happens is a new cavern forms in there, and then the last thing is that it collapses. And so you end up with this very complicated pattern. Most geologists today look at this and it doesn't look like what we're used to drawing. And most geologists think, that's really a screwy idea. Boy, when I took the time to really examine it carefully, I came to realize Steno was absolutely right on, and he was making the same kind of observations that I make, and his theory was not quite what I do, but I've got 300 years worth of people that have thought about it between him and me, so naturally I'm going to think a little bit differently. But it's wonderful. And the point here is that for the first time ever, Steno was using rock strata to infer a history. His history isn't quite right, but it's close. So that's Steno. And he should have gone on. He should have written the dissertation. It would have been the greatest book ever written in geology, I'm sure. It would be the Darwin's Origin of Species of geology if he had written it. But he didn't write it for an interesting reason. So he was, having been born in the 17th century in Denmark, as you can imagine, he was a Lutheran. He'd grown up a Lutheran. And this was the time he was actually there when the 30 Years' War was going on. Do you remember that the Reformation started with Luther and his nailing the theses on the door in 1517? 101 years later, things had got to the point where there was a terrible religious war, basically in Germany, called the 30 Years' War, that ran from 1618 to 1648. And that was the era that Steno lived in. And so he grew up as a Protestant, as a Lutheran. And when he went to Florence, he was in Florence for quite a while with these terrible people, these just awful people, these papists. They were Catholics. I mean, this was shocking. But as time went on, Steno apparently came to respect more and more these scientists and the Medici in Florence, and after a while he converted to Catholicism. It sort of meant he couldn't go home to Denmark, but he continued to be very welcome in Florence. And the church, the papacy, realizing what a really major intellect this man was, they quickly made him into a bishop. And then, since he spoke the languages of the north, Danish and German, they sent him off to the North countries to try to help recover these Protestants back into the fold of the Catholic Church. And so Steno spent the rest of his life in Germany trying to undo the Reformation, unsuccessfully, and as a result he never wrote his book. He never wrote the dissertation about layered rocks, which saddens me enormously. But let me show you about what happened. So in Florence, there is a church called San Lorenzo. And we went there last summer to look at it because it contains the tomb of Nicholas Steno. And Nicholas Steno, the bishop, has been beatified by the church, which is, my understanding, is that sort of the first step on the path to becoming a saint. So he is not Saint Nicholas Steno, but he is the blessed Nicholas Steno. And there is a chapel there. This is his tomb, and this is a stained glass window on the wall behind it. And people come there to venerate the tomb of this blessed bishop of the church, who also happens to be the founder of stratigraphy. Now that's a pretty unusual situation. And so in 2004, there was an International Geological Congress was held in Florence. It's held every 4 years somewhere around the world, and it hadn't been held in Italy for more than a century, but they held it in Florence. And at that thing, a friend of mine from Bologna named Giambattista Vai led a pilgrimage to the tomb of Nicholas Steno. Sadly, I couldn't go. I had to be in the field that day. I just was so sad I couldn't go. But they placed a marker there. And so it is to Nicholas Steno, all in Latin, which I read not at all, but I can recognize that here it says, the inventor of stratigraphy and crystallography. And underneath it, it says something like, geologists from all parts of the world in the 32nd International Geological Congress in Italy, they came to commemorate this man who is both a major figure in the church and a major figure in geology. So that's Nicholas Steno. Any questions? Somebody's asking any questions. All right. Michelle, thank you.
So the models that he proposed?
Yeah. Uh-huh.
Are those basically the ones where you discussed the earth and whatever's on top of it?
Yes, that's an extremely good question. It would take about an hour to discuss it, but let me just go back there for a second and, whoops, I got way off here. Hold on a sec. Let me go back and show you how it works. Okay, so here is this one. So what Michelle asked is whether those collapses are like where the East African Rift Valley forms, where the continents are starting to break up. It is actually in a sort of a small way. We now know that this is due to extension. It's not due to the breakup of a continent. It's a smaller scale extension. But I should point out to you that he had a problem explaining this, because Steno, who was just inventing this thing, all he knew about Earth history was what everybody else knew, what was in Genesis. And so look what he had here. He had one set of layers, and they were full of marine fossils, so they had to be deposited by marine water. So there had to have been a time when there was water covering the sea covering the land, and then after this collapse you get new strata there, and they have marine fossils in them. So what he had to explain was that there had been two incursions of the sea into what is now dry land around Florence. So the only thing he had to go on was the Bible. And so his interpretation was that these original ones were deposited by the original universal flood, when the earth was being created, when there was thought to have been sea everywhere. The sea had been created, the dry land had not yet been created. Then the dry land gets created. Now these things are happening. And now you get more marine strata. What is that? What do you suppose that was from? Noah's flood, exactly. And so that was his interpretation, and it fit pretty well with what the Bible was saying. So it only came much later that people realized that this wasn't right. And I think maybe that's a good lead into what I want to do next, which is to take you to Gubbio. So you guys have read the T-Rex and the Crater of Doom. So some of this will be familiar to you, but maybe there'll be a slightly different take on it, or you'll get to see more pictures of it at any rate. So let me show you what happened when we got working on these kind of rocks, not very far from Tuscany. We're 100 miles from Tuscany or something like that, in the 1970s and the 1980s. Well, there are bedded rocks, horizontally bedded rocks, and you can see those here. All right? So you can see the layers running across this. This is exactly what Steno said. Rocks are deposited originally horizontally. Well, this is a picture I referred to before, and I wanted to get it in for you to see. That's my father. And when he came to visit and see what these rocks were like when we were working on the extinction business, and remember, he had a problem with the fact that the beds were tilted. He said that's going to be hard for physicists to understand because they like things simple. So he leaned over there, and I turned the camera, and so that's the picture for physicists, but this is what it really looks like. And so we were trying to understand these rocks, and they have this wonderful collection of fossils in them. Some parts have big fossils. So here's my friend Don Domenico. He's the priest in Piobico, and he was our best friend for years and years there. He's an absolutely wonderful amateur paleontologist. And these are some of the fossils that he collects. See this great big spiral thing? That's an ammonite, and it's another little ammonite on top that he's sort of cleaned away the matrix so you can see what's there. And all through here, his upstairs of his church is just packed with ammonite fossils. So he collects them in the mountains in the summer, and he cleans them off in his laboratory in the winter. But these are big fossils. And these are the kinds you can walk around with, and you can say, oh, I identify that. These rocks must be this age, because in the years after Steno, geologists had gone and they'd found lots and lots of fossils. And what they'd see is that you have a big series of layers like that. The kind of fossils that are in them change gradually as you go up. And that's the evidence that evolution actually happens. And even before evolution was understood, geologists had learned, and we're talking now about 1800, geologists had learned that you could study the fossils. If you had gone to one place and figured out the sequence of fossils, and then you go over here someplace and you find a fossil and you can look at it, you say, it's the same as that one over there, then you can say this rock was deposited at the same time as this one because they have the same fossils in them. And that work was done using these large fossils, ones that you can carry around in your hand like Don Do has. But that didn't work for all kinds of rocks. And as a matter of fact, those limestones that my dad was looking at there don't have any big fossils in them at all. There's nothing that you can get, nothing. I mean, I've looked at those things for 40 years, I suppose, and I have never seen a big fossil in them. But they're full of tiny fossils. And the tiny fossils turn out to be much better for dating rocks than the big ones. So here they are. So these are the kind that we use in our limestones. They're called foraminifera. They're single-celled eukaryotes. And they float in the ocean waters, and they're nasty little predators. You know, these things are pinhead size or smaller. The smallest ones you just can't even see without a microscope. The biggest ones are sort of pinhead size, kind of a millimeter. And they are these funny little bulby things like that. And I'll show you another picture in a moment. But these are living ones. These are not fossils. And this is what they look like. They have these little tiny holes all over the surface of their shell. And out each hole comes a long, thin filament. it's called a pseudopod, a false leg. But these things are these are little things of protoplasm, little streamers of protoplasm, and it looks very pretty. But if you are something the same size and you brush against that, they catch you. Like this little guy here is a copepod, and he accidentally brushed up against a foram, and he's been dragged in, and he's going to be eaten and digested by this foram. They're nasty little creatures. But their shells are absolutely the best fossil tools that paleontologists have for correlating marine sedimentary rocks over long distances. And that's what we were able to use at Gubbio. The problem was, however, that this is what a foram looks like if you get it out whole. You know, if you can wash off, if it's in some clay and you wash off the clay, that's what it looks like, and then there's been a scanning electron microscope picture taken. But our rocks are so hard that you can't get these fossils out whole. And so this lady here, my friend Isabella Premoli Silva from Milano, she was the person who figured out, when she was still very young, how to cut a very thin slice of one of these limestones so that you can see the foram in there. And she was for a long time, she was the only person who could do it. She was so skillful. She could identify these things from this cross section without having to get it out whole. Let me show you why that is hard. Supposing that you're looking at a friend, okay? I can see somebody here, somebody there. I recognize them by their face, okay? Now supposing you can't see their whole face, supposing all you can see is a profile, supposing they are walking in front of the projector and you see their profile on the screen. Well, if you see the profile like this, you're very unlikely to be able to recognize them. Maybe if you get it just right and you can see them in this profile, you see nose and lips and things, you may be able to recognize who it is. And it's the same thing here. She had to really know these things inside out, and she had to cut lots of these thin sections of the rock in order to get any that were in the right orientation so that she could recognize them. But Isabella learned how to do that, and it was her ability to do that that made it possible to date these limestones that Dad was looking at, and to do all the things we did with it, magnetic stratigraphy and the work with the Cretaceous-Tertiary boundary. So let me just say a moment about the Cretaceous-Tertiary boundary. Here it is, and it runs like that, and you know some of these people. You know Millie and me, you know Roland, you know David, my grad student, and this is Sandro and Paula. He was my PhD student here who started his own institute in Italy. So if you have indeed read T-Rex and the Crater of Doom, you've met Sandro and Paula, but we were there last summer. And this is, you see how it's tilted? And this is the Cretaceous-Tertiary boundary here. So these rocks were all deposited in this order, older, older, younger, 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 like this, up to this point, while all of those kinds of animals, including most of the forams, including dinosaurs, including a lot of other things, while they were still alive, then something bad happened at this level right here, and after that, many kinds of organisms are no longer alive. Now, we can't find out about dinosaurs here because these were marine rocks, but we can find out about the forams. Oh, here's just another picture with Roland, and this is Darren Green from Microsoft Research, who has been the guy who's been supporting Chronozoom. So if you like Chronozoom, Darren's the guy to thank. All right, so let's go back to this picture. So here's the tilted one, and here is Cretaceous there, and there's the boundary where the mass extinction is, and there's the Tertiary above it. Okay, just to show you what we found remind you what we found and published in 1980, here's what it looks like if you look at thin sections. So this is a piece of rock. It's about the size of a domino, I guess. And this is the first bed of the Tertiary, this is the last bed of the Cretaceous, and this is some clay in between. And we've just put it down on top of a couple of photographs taken through the microscope. And these are at the same scale. And so you can see this is just full of big forams. And those forams and their relatives have been present in every piece of rock that you break open for, like 150 meters below this down the section for about 30 or 40 million years worth. Up here, those guys are just gone. and they never come back. Now you see there are some forams here, so some of these little tiny guys, they did get through the extinction. If they hadn't, forams would be extinct. We wouldn't even know what they were. We wouldn't know about those clouds of tentacles trapping poor little creatures. But this is what the extinction looks like. And it was actually Isabella who first showed this to me in the field and said, say, we spent a lot of time doing field work when we were working on this section. One time she said, I want to show you something. Come and look at this. This is a mass extinction. And she showed me this in the field. So then we went on and we sampled it, and we brought samples back to Berkeley, and we measured them for iridium. And so here's the iridium picture here. So this is a meter there, and this is that boundary layer. And this is the amount of iridium, and the peak here is that's 200 parts per trillion. The peak's at 3,000 parts per trillion, which means it's 15 graph widths out there, out in the outside the window someplace. And this was the original evidence for the impact at the end of the Cretaceous. And so this was the idea. We thought this had happened someplace around the world and caused the mass extinction. And eventually, and that was in 1980 that was published. And in 1991, the crater was discovered in Yucatan. This is a painting of what it would have looked like then. You can't see it now because it's all covered by younger rocks. But this is the sort of thing that came from what Steno started. Basically, the notion that if you can read, if you recognize that layered rocks are a recorder of Earth history, you can read all sorts of things in there. And this is just the part that I've been involved in. But we could talk for not one class or one course, or you could spend your whole career learning all the things that people have found out about the history of the Earth from layered rocks and finding out more, which is what I've chosen to do. Okay. Any questions on that? I guess we're going to go on to the last of our places. Yeah, Josh.
Well, I don't know if you said this, but I was wondering who was the first person maybe who said, oh, these rocks are actually older than the Bible said. When did they start to...
I didn't. I sort of... that's really an important part of the story, and it goes back to a man named James Hutton. We actually have a good bit of time, so what I'm going to do, I think I will just show you that because it's really an important point. So pardon the unsmoothness, but I'm going to have to go and find a different slide here that I wasn't going to show. It's toward the end somewhere. This one here. Okay, so this guy is generally credited with being the discoverer of deep time. His name was James Hutton, and he was a medical doctor in Edinburgh in Scotland. Almost all these early geologists had something to do with medicine because that's the scientific thing that you did in those days. And so this is his fabulous discovery. This is at a place called Sicker Point in Scotland. And he knew now that sedimentary rocks had been deposited in horizontal beds because Steno had already discovered that. And what he saw here was a series of beds which are not horizontal, they're literally vertical. You see that? And on top of them is another set of beds which are not quite horizontal, but almost. And this is what geologists call an unconformity. And so what Hutton realized was that these beds that are now vertical had been deposited horizontally. And somehow or other they had been tilted up completely vertical, so they went like that. And then the upper part had been eroded. And it had eroded right down to this level. This was how far the erosion got when it stopped. And then more sediments were deposited on top of it. So an unconformity is a place where you have originally horizontal beds that have been tilted. They don't always have to be vertical. They might be tilted like that. And then they've been eroded off and more horizontal beds have been laid on top of that. And what Hutton's genius was to realize that this was evidence that an enormous amount of time had passed in order to have these, what had been marine rocks had to be up above sea level in order to be eroded off. Then they had to be back down below sea level to get more sediments deposited. And now those sediments are being deposited, they're back up above sea level. What Hutton realized was that the history of the Earth has been very cyclical. Deposition, deformation, erosion, more deposition, more deformation, more erosion. And so he was the great prophet or the great supporter of a cyclical Earth history. And his great book, almost nobody can read it. He seems to have written it in a great hurry, and it's almost unreadable. But in it, there was one phrase that all geologists know. And he said that after studying this rock record like this, he could see no vestige of a beginning and no prospect of an end. In other words, he could see no reason why these cycles hadn't been going on forever. So when you think about that, it seems that Hutton, if he wasn't exactly saying, he was thinking about an Earth that is infinitely old. No vestige of a beginning, no prospect of an end. Well, we know now that that can't be. Anybody who understands the second law of thermodynamics knows that you can't have a perpetual motion machine. And an Earth that kept going and cycling forever would be a perpetual motion machine. So Hutton carried it too far by thinking that there really had never been any beginning and there was never going to be any end. But he's justifiably credited with having understood that the Earth is enormously old. So this is now, we're talking about, well, he died in 1797. So at the beginning of the 19th century, the 1800s, the 1810s, that was when geologists started going out and doing what I was describing before, finding all of these fossils in layers and figuring out which ones came, what order they came in. And at that point, they had the understanding from Hutton that the Earth was extremely old, much older than the Genesis timescale. And from Steno, they had the tools for figuring out Earth history. So that's how all that happened. So thank you, Josh. That was a perfect question. Okay, let me go back and pick up again where we were. Okay, so this is where we were. That this is the point when, this is what we really discovered in Gubbio. So now what I want to do is to tie this together by taking you on a trip to our fourth place, which is Siena, our fourth and last city. This is a place that Millie and I have been a couple times in the last few years and just learned the most interesting things. So Siena is another town in Tuscany, not that far from Florence. So this is where Steno discovered that history is written in layered rocks, and I'm sure it's not the case, but for my own personal amusement, I think the layers of black and white in the Siena Cathedral are reminders that Earth history is written in layers, just as the building of a cathedral is written in layers. Okay, but I want to take you to a different place in Siena that almost nobody has ever been to from outside Siena, and that's this place. It's called the Accademia dei Fisiocritici, and that means the Academy of the Critical Thinkers about Nature. Lovely old name. And this was founded in 1691. This was a very, very early natural history, geology, paleontology research center and academy for talking about these things. So you see here, we're not long after Steno, we're 30 or 40 years after Steno, this was founded. And people started collecting fossils and studying them and describing them and naming them. And so on the outside, this building is not very prepossessing, but it is an old monastery. And on the inside, it's both a wonderful architectural treasure, and it also is a natural history museum with things like this. I guess that's a whale, right? And so in the academia, they have both these fabulous things that go way back to the beginning of geology and very modern scientific exhibits. It's a teaching museum like the Exploratorium or the California Academy of Sciences. So let me take you and show you some of the things that we found inside there. Well, we discovered that there had been an abbot when it was still a monastery who was a scientifically oriented man whose name was Ambrogio Soldani. So if you look at that, you see we're kind of 100 and some years after Steno. And I discovered, I didn't know this until we went, that he is the inventor of micropaleontology. And micropaleontology is the paleontology that studies those little microfossils like the forams. And they are, beyond a doubt, the most valuable fossils for determining Earth history. And he was the guy who figured it out. Actually, contemporaneously, there was another man in Bologna, but they were at the same time and independently, they started looking at these microfossils. And so when we went there, we had this wonderful experience. So here are some geologists from the academia, and what you can see is these old-fashioned museum cases with wonderful specimens, and it's got a real air of old authenticity to it. And we were standing here, and there was this great polished case of wood. And they pointed to, on top of it, there was some inlaid wood. And what that says is conchiglie microscopicae. This says microscopic shells collected by Soldani, born 1736, died 1808, Academia of Physiocritici. But that was, when I saw that, I realized this was the guy who started the micropaleontology that Isabella and I and all of our other colleagues used to study the rocks at Gubbio. And it turns out that this guy spent years doing this. He spent maybe 30 years. He was fascinated by these little microfossils. And probably people didn't know they were there, but he'd probably taken some sand from somewhere in Tuscany, and he was looking at it under a microscope. He had a primitive microscope, and he started seeing, hey, some of these things are not grains of sand, they're little tiny shells. And there was a whole world to be discovered under the microscope, because the largest of these things you can see with your naked eye, but you can't see any details. You have to have a microscope. And so he spent these decades studying these things and drawing them in great detail. So here are drawings. These things, you know, a good I can tell roughly what these are, and a good micropaleontologist can tell you the species on these things. They're beautifully drawn. And he published this great treatise. And of course, he didn't have evolution to tell him what he was doing, because evolution didn't come in until 20 years after he died. But he was making these descriptions. That's what they did in those days. And so to me it was just fascinating to stand there and kind of look at the life's work of this guy who started doing the things that have been so valuable for me. And then everything suddenly came together in a way that I absolutely would not have expected. I couldn't have imagined this. What happened was that we had spent some time admiring that case, and actually they opened the lid and showed us all these tiny little bottles that he had. He'd thousands of these bottles in which he'd taken samples and collected them and washed away the sand and the silt and collected the little microfossils and studied them. It was just a life's work in this case for these beautiful little things. And when we finally got tired of that, we went out into the next room with the geologists from the academia, and one of them said, I want to show you something really special. Right now, sort of the hair is standing up on the back of my neck. And what he showed us was this. This is a meteorite. Okay, now you've all seen meteorites. It's not a big deal. You can go to any museum and see them. But this meteorite fell just south of Siena, visible from Siena, in the evening of April 16th, 1794. And the Abbot Soldani at that point had just finished his studies of microfossils. He had just published that enormous, there were several volumes of all of these wonderfully drawn, engraved plates of what these microfossils look like. And he must have been standing out there. It was in the early evening. In April, it was probably a lovely evening in Siena. Everybody's outdoors having a cafe or probably not a gelato in those days, but at any rate, something like that. And all of a sudden, the sky to the south of Siena was lit up by this huge flash of light that went on and on. And then the thundering roar started coming in, and something had fallen from the sky. So Soldani hurried out there the next day, I guess, and I imagine what he did was he'd ask peasants here, what did you see? And the peasants said, oh, one of them, it's just a rock fell through my chicken shed. And so Soldani collected all of these pieces of the meteorite. And nobody knew at the time what this was, because this is kind of like fossils. Remember, there's a big debate over fossils. Are they the remains of animals or are they sports of nature? There was also a debate going on at this point about whether rocks could ever fall from the sky. And most of the wise scientists of Europe said, impossible, impossible, can't happen. Well, Soldani saw it happen. And so he collected all of this material, and very generously he sent it to chemists from all over the world. And chemistry was just getting started then, analytical chemistry was not very skilled at that point. But he wanted to find out everything he could about it. He was so generous with these pieces that now there's only one tiny little piece left of the Siena meteorite in the Accademia in Siena. This is not it. This is actually, I think, from Milano or someplace else, because the one in Siena isn't as good a piece as this. But people from all over the world studied these things and went over his reports. He published, the last thing he did in his life was he published this great report about this fall of rocks out of the sky in Siena in 1794. And the conclusion was, after all of this was done, yes, rocks can fall out of the sky. There's something new, meteorites. They don't have anything to do with the Earth. They came from somewhere else. And it was an enormous shock, intellectual shock through this sort of early scientific Europe. But can you imagine the sense that I had sitting there realizing that the guy who invented micropaleontology, which had let us date and understand the impact that caused the extinction of the dinosaurs, had also been the guy who showed that meteorites can fall from the sky. That's my story. Thank you. Yeah, Ricardo. Yeah, the cube. I'm sorry, the cube is a 1 centimeter cube. It's just for scale. Yeah.